So let's think now back in time to the oldest mathematical evidence that we can find in our archaeological digs. The oldest discovered mathematical object is considered to be this piece of baboon fibula dating back 35,000 years before Christ. So minus 35,000 years. It's a simple bone with a bunch of notches. In fact, exactly 29 of them. Now, 29, you can think about what that number is interesting for. And again, remember your biases. So as a mathematician, I look at that 29 and I think, well, that's a prime number. Would prime numbers have been interesting to people recording notches on a fibula of a baboon? What might have 29 meant to them? Think about that as we talk about the oldest interesting mathematical object. I say interesting here because this simply has more information and therefore maybe we can deduce more things from it. This object is known as Ishango bone. This is also a fibula of a baboon, but now it has more structure to it and in fact is just a little fancy all around. It has a sharp piece of quartz affixed to the top of it so that you can use that as the actual engraving tool. You can take out this little piece of quartz and make your next engraving and move on and so on. It has 3 rows of numbers on it, and this is the R in sort of a pictorial form. Okay, the bone itself dates back 18 to 20,000 BC. And so while it's younger, let's say, than the previous bone, it also has more information on it. So let's take a look at these numbers. And we can theorize why the ancient people might have been interested in making these particular notches in this particular pattern with these particular things. So again, my mathematical eye is immediately drawn to this particular row of numbers, 11, 13, 17, 19. Notably, they're all odd, but 15 is missing. So whoever the ancient author, they decided to exclude 15 from this list, which again immediately makes me believe that this is somehow a row of prime numbers. Some mathematical historians will say that this is well before prime numbers were understood. The first sort of find that we think about as people understanding prime numbers was about 500 BC. So of course, that's quite a bit later than that. This is when the division began being really understood. But really, as witnessing my child putting little marbles in rows, it's fairly easy to see that, for example, I can put 6 in 2 neat equal rows of numbers, and I can do no such thing with the number 5, no matter how I arrange my rows. There is never going to be exactly a nice rectangular formation of them. So whether or not you believe that these are prime numbers, that's up to you. Other historians quite reasonably suggest that this represents the tracking of a 6-month lunar calendar. And this is really quite believable, right? Because we can think about what would people be interested about the way back when. And of course, solar movements and moon movements is something that cannot escape an attention of any human or animal or a plant or any really any living creature living under the sky. This is something that we notice, and if we can in fact make notches, this is something one might be interested in tracking. This also somehow works quite well with the previous bone that I showed you that had 29 notches on it. And of course, we know that 29 is an approximate length of a lunar cycle, which led other historians to suggest that the creator of the tool may have been a woman tracking the lunar phase in relation to the menstrual cycle, right? This is something that is completely reasonable to believe, but because we have no other evidence other than the notches on this bone, all of these theories sound plausible to some people and implausible to others. Let's take a look at other types of things that we see dating back that far. We're then beginning to see a much more intricate Engravings, such as geometric designs, they appear all over the world in Egypt and Mesopotamia in numerous shapes and forms. We actually have lots and lots of these as archaeological finds. The oldest artifacts actually date back 70,000 years, which shows the human interest in shapes and how they work with each other. So here, for example, we see triangles, which are not so popular in nature, but the triangles form regular hexagons, which of course can be seen, for example, in a honeycomb, and then altogether form an even more extended, beautiful geometrical design. We then see geometry appear in another form, in particular in the use of shape. Fired clay tokens were used by people around 8000 BC to record products of farming or to record exchange at markets. So here we have complex tokens from Susa, Iran, where we have some evidence to suggest that they represented different things to be kept track of at the market or, again, as a product of your farming. A parabola, for example, represents a garment. So if I have produced 2 garments, I can record it with 2 parabolas. Or when I sell it at the market, I can keep track of my stock. Now, tokens are believed to have been instrumental specifically in separating the idea of a number, the abstraction of it, and the written word. The intellectual leap from the concrete idea of a number, for example, 2 tokens in your hand, to the invention of a symbol or a word actually took many ages to come about. So here we get to think about the difference between all of these ways to represent a number that in modern society gets taught to us so early on that we sometimes have trouble separating it. And here I find it useful to think of the etymology. Where do the words actually come from? Let's take a look at what the words actually mean. The word calculate comes from the Latin word calculus. That should sound familiar. That actually means a pebble, because when the first people started to calculate things, they were likely doing it with pebbles. The word thrice, which I find we don't use often enough in English, actually means 2 things. It means 3 times, and it also means many. And this is similar to various other tongues, where, for example, in Latin, tre means 3 and trans means beyond, with the words actually very similar in pronunciation and in writing. In French, trois means 3 and tre means very or many or much, right? So again, we see the similarity in the words, pronunciation and writing-wise. Some languages have words for every color, but no word for color itself. So this is where we see the distinction between the specific and the abstract. Similarly, there are languages that have all the number words, but no word for number. As an abstraction, it is either not needed or not yet become needed. Even today, there are generally small tribes in Amazonia which only have words for 1, 2, and many, or they only have words for numbers up to 5. Why do you think that is? Well, up to 5 is probably easy to think about because we have 5 fingers in our hands. But why don't they need more words? I should also point out that their usage of these words is actually much more complicated than the paragraph first makes you believe. So, for example, if a person from such a tribe wants to say 7, it's not that they are unable to, in fact, pass on the information about, let's say, 7 apples. They can, but they will only use their existing words. So they would say 7 is 2, 2, 2, and 1. Their system is additive. So if you add all of these numbers together, you will in fact get 7. The word for 7 isn't needed because it's not used often enough. And when it is needed, you can use whatever things you have. Words for 1 and 2 are used all the time, so they get a special number word attached to them. Let's think of, for example, of English and number words in English. We have 1, 2, 3, 4, all the way to 10. And our system is base 10, so you would think that this is when we would start switching from a special word to a composite word. But no, English gets a special word for 11 and a special word for 12. Only starting at 13 do we move into this teen structure of saying that this is 3 teens. 14, of course, is then 4 teens, and so on. In Russian, the other language I speak, the system is much more base 10. So we have number words all the way up to 10, but starting at 11, we immediately move into the corresponding teen structure. So, for example, we have word for 1 is один, and word for 11 is одиннадцать. Один, одиннадцать. Два, двенадцать. Три, тринадцать. So the system is already dependent on the 10 and the previous number. Consider the Halkomelem language, the language of the Stolu people of the Fraser Valley. Here we have a beautiful number booklet that was produced as a part of the Fraser Valley Mathematics Education SCUP. SCUP is a Stolu word for gathering. And we can see that the way that the words are formed in Halkomelem is, again, very base 10 oriented. We have the word for 1 all the way through 10, but once we hit 10, we begin to see the structure that suggests that the people were very aware that 10 is where they want to stop. So after 10, we have 10 and 1 as 11. 12 is 10 and 2, and so on. And once we get into the multiples of 10, we once again use the corresponding number less than 10 to represent, to be part of the number word. Feel free to look for the booklet on Google or on Blackboard to explore the language further. This type of thinking really makes you realize that the language and the mathematics are intimately connected. If you speak French, think about what happened there with the numbers 1 through, let's say, 100. How come 80 in French is actually 4 times 20? Why is that the case? Why is it important to preserve that as a language? Here's another fun story. The word tally comes directly from French, from tailler, to cut. The medieval Latin word is also to cut, twig. And tallies, the way that we think about them now, to tally something up, actually play a really important role in the formation of the Bank of England. So in 1690, England was defeated by France during a battle of the 9 Years' War. England had no choice but to basically build a very powerful navy for which the government had no money. So they decided to gather money from the people. The subscribers to this loan were incorporated under the name of Bank of England. The lenders will give the government cash and issue notes against government bonds, which can in turn again be lent. In 12 days, the English people managed to actually raise 1.2 million, well, not quite dollars as I wrote, but whatever currency was going at the time. Only half of that was actually needed to rebuild the navy. The process of lending was the following. So the lender, someone who lends bank money, the amount was cut on a stick with actual tallies. And then the stick was cut in half. The piece that was kept by the bank was called a foil, and the other piece that was held by the person who lent the money was called the stock. That was basically the receipt that was issued by the bank, and the holder therefore became known as a stock holder. This terminology still survives today, right? And so when the holder of the stock decided to get his money back, they simply needed to bring their stock in, and then it needed to be checked against the existing foil at the bank. The word foil hasn't really survived to this day, but the words stockholder and the words check actually have. In the synchronous session, we will talk about math problems from the ancient world. So here, There is no fancy algebra allowed. Let's think about how we can solve these from what we would say, for example, first principles. What tools do we absolutely need to solve some of these problems? But the other thing that I actually want to focus even a little bit more than math is the content. The content and the context. As we read through these problems, and we will talk about their actual sources later on, but note the years and note the different cultures. As you read through these problems, think about, why would anyone ask that? What was the goal of these problems, and what was the bigger purpose? Is it something practical that was asked? Is this something that a person would face in everyday life? What purpose did these problems have? Why did the humanity at the time need to solve these problems? Don't think about math alone. Think about it as embedded in society, in the time period and the culture. What do you think was the purpose of these problems?